today is like a big day. Today is the day with we get to see how, why, and graphs and all the fun stuff about limits. So yesterday we discussed that a limit is a rate of change. And a limit represents the instantaneous rate of change. And a limit has properties. And those properties are that if you take the limit of a constant, it's always equal to the constant. If you take two limits and add them together, they equal the sums of the two limits if you took them separately. And that's going to be true or hold true with graphing limits and looking at limits of graphs. So limits can exist, they can fail to exist, they can exist from one side, and they can exist from two sides. So today we're going to talk about all the properties of limits and how and when they exist or fail to exist. So left and right hand limits. When we looked at the table, you were looking technically at a limit from the left and a limit from the right, approaching plus the limit of the value in the middle. So when we were looking at our table examples, we were looking at a limit from the left, a limit from the right, approaching a value in the middle. All right. To make sure you see the difference, the emphasis on a left-hand limit is the negative after the A down there. And the emphasis for a right-hand limit is the positive. So a left-hand limit says that we're looking at the limit as x approaches A from the left. And that's what that negative implies. And a right-hand limit is the limit as x approaches A from the right. And that's what the positive implies. Because if you think about a number line, as you approach from the left, you're coming from the negative side. And as you approach from the right, you're coming from the positive side. So that's where the negative and the positives came into play. Even if you're not approaching like 0, you're approaching any number from the left is negative and right is positive. A function, and this is huge, Theorem 3 is importante. Theorem 3 says a function has a limit if and only if the right hand and left hand limits both exist and equal the same value. So the limit as x approaches A is equal to L if and only if limit as x approaches A from the right equals the limit as x approaches A from the left equals L. Okay. So we can show some graphical examples of left and right hand limits. An example of a limit from the left. So you could draw almost any function you want. I'll just draw a quadratic. So we have this quadratic function. It has a point at A and has a limit at L. So to talk about the left-hand limit, we would say the limit as x approaches A from the left of f of x equals L. Because as we trace the graph from the left, getting closer and closer to point A is getting closer and closer to L. Similarly, the limit as x approaches A from the right for f of x now means you trace your graph from the right side. It doesn't matter if A is open or closed. As we trace that graph from the right, it's once again at a height of L. Yes. Yes. Yep. I just wanted to show it didn't matter if you found A on like the left or right sides of the graph. Yes. So the left and the right all come from the direction you're tracing the graph. So if I were to have traced this graph from here, it would have been a left-hand limit. When you trace the graph from this side, it's a right-hand limit. Wait, no. Good point. Like actually like point to what you're saying to me. But don't actually touch because the board will move. Yes. So, right, like if I trace this graph coming down like I am in red, that red would have been a right hand limit. It's the direction exactly that you approach the point. Yes. Because you're coming from the negative to the positive. So where are you coming from? You're coming from the negative. So it's the left is coming from the negative. The right is coming from the positive. Let's talk about when a limit would fail to exist. So in that definition for when it must be true, we said the left must equal the right. So a case where it would fail to exist would be the left-hand limit does not equal the right-hand limit. And an example of that would be jump discontinuity from a piecewise function. Another example would be if it's increasing or decreasing without bound. So that's an example of a vertical asymptote. So a vertical asymptote will be where a limit does not exist. And an oscillation. And we're going to talk about 3 and 2 and 1 all today. So the best way is to explore. The best way to understand is to explore. So in part A, it says the limit as x approaches -2. So I'm going to go to my graph and I'm going to look for -2. So that's on this axis right here. And it says -2 from the left for function f. So f is the upper curve. Coming at the graph from the left means I'm starting here and tracing in. So the limit as x approaches -2 from the left is 1. The limit as x approaches -2 of f of x from the right. So now I'm going to trace my graph coming in from the right. And I see that it is at the same height as it was from the left. So it is also equal to 1. So the left-hand limit equals the right-hand limit. Therefore, the limit as x approaches -2 of f of x is 1. Now, it's important to note that f of -2 is not equal to 1. F of -2 is equal to 2 because it's where the closed circle is, not the open. So it's important to note that a limit does not have to equal the function. Let's talk about g. The limit as x approaches 1 from the left of g of x. So here's 1. Approaching 1 on g from the left puts me at -2. The limit as x approaches 1 from the right. So here's my g function coming from the right. It's at -1. Does the left-hand limit equal the right-hand limit? Therefore, the limit as x approaches 1 of g of x does not exist. And again, this is an example of jump discontinuity. We're going to talk all about discontinuity. It used to be in 2-3, so I'm thinking in 1-3. Don't worry about that. Okay, out of curiosity, What is g of 1? What's g of 1? Go ahead, Corey. Perfect. Yesterday we talked about properties of limits, and we said that you can add, subtract, multiply, divide limits, and you can do them as their limits or separated. So we can, in example G, look at the limit as x approaches -2 of g of x and add it to the limit as x approaches -2 of f of x. And since g is being multiplied by 5, we're going to put that in front because we're going to find the limit first and then multiply that value. So the limit as x approaches -2 of g of x. So I'm going to go to -2. We're concerned with everything at -2 in terms of limits. So the limit as x approaches -2 of g of x is -1 because the left-hand limit and the right-hand limit both approach that point. We already discovered the limit as x approaches -2 of f of x in example C, which we said is 1. So 5 times -1 is -5. -5 plus 1 is -4. No. The limit as x approaches -2 is 1. Exactly. Yep. You got it. In H, the limit as x approaches 1. So now we are concerned with 1. Exactly. So if g fails to exist, then the limit, whether it's being multiplied or not, fails to exist. Therefore, the limit as x approaches 1 of f of x times g of x does not exist. Yes. It still not exist. Because if it fails to exist at g, you can't add it to f. And then in I, the limit as x approaches 2 of f of x over g of x. So now we're talking about 2. So at g of x, the left-hand limit and the right-hand limit are both approaching. Good. And at f of x, no. But it's like, if you're approximating, it'd be like 1.5. However, this is different than does not exist. If you try to divide by 0, what's the slope of a vertical line? So if you try to find a limit and you get a number divided by 0, it's undefined. that it's outside of a domain, that like it exists, because there are points, they exist, but it's undefinable because you're dividing by 0. So like the rate of change does not occur. Because the difference is, does not exist, it doesn't exist. There is not a limit to exist. Whereas undefined, it's there, but we can't process what it means. It's more like unfathomable. All right, find the limit using a table and then confirm it. Yes. That means no solution. So if you had something that did not have a solution, then yes, but those are different again. That's different again than what we just talked about. No. They're all three different. For a limit, absolute values equal to a negative. So like if you had the absolute value of x equals -5, it's impossible to take the absolute value of a number and have it equal a negative number. So this would be a case of no solution. Because if you solved it using like our absolute value rules, yeah, you'd get x equals -5 and x equals 5, but they're what we call extraneous solutions, because you can find a solution that's invalid and therefore no solution. All right, sine x over x. Go ahead and graph that real quick. See what it looks like on your graphing calculator as a graph. Because this is a special function in calc. So it should look roughly, let's erase this line and I can fix that. Oh, hit zoom like 6 or hit zoom trig. Zoom trig I think is zoom 7. All right, so just looking at that graph, what do you expect the limit as x approaches 0 to equal? Use your tick marks to try to help you figure out what the height is. 1. It does actually equal 1. If you go to your table, hopefully most of your tables are still set up with like the -0.1, -0.01, -0.001. And we see that it also approaches 1, right? This is something you have to memorize. Because if you plug into this, the sine of 0 is what? Well, just in general, what's the sine of 0? Yeah, so this is that indeterminate form again. So we don't have like an algebraic way, really, to simplify it. So this is what we call a function you memorize. And there's actually 3 more we're going to add to it on like Tuesday, maybe Monday. No, Tuesday. Okay. So the limit as x approaches 0 of sine x over x is 1. You're just going to keep that in your brain. There are limits we can't find by graphing them. So this is a case, remember I said there are 3 reasons a limit fails to exist. You have jump discontinuity, you have a vertical asymptote, and that vertical asymptote was like the limit is f of x over g of x example, because it did not have a slope that was defined. And then we have an oscillating function. So in this example here, that pink graph is an oscillating function. And that pink function is cosine of 1 over x. So without the x squared, we could graph cosine of 1 over x. And see that it gets really oscillating towards the middle. And then if you put the x squared on it, it increases that oscillation exponentially because now it's trying to square even more. So this image right here is an extremely zoomed in image of the graph of x squared cosine 1 over x and the parent function x squared and its reflection. So the sandwich theorem, it's also known as the squeeze theorem. So you might also have it read to you as the squeeze theorem in our textbook. Basically says that if you have a function that's limit is oscillating, it does not exist. But what we can do is squeeze that function between 2 functions we know do exist to find the limit. So we're going to squeeze this function here. We have x squared sine 1 over x. If you plug into that, you get the limit as x approaches 0. Plugging in, we get 0 squared, the sine of 1 over 0. Well, again, we know we can't divide by 0. So that part of the problem is undefined. So we have to find a way to find the limit. And that way we find it is the squeeze theorem. What is the domain and range of the sine function? What is the domain and range of the quadratic function? So the sine function has a domain all reals and a range of -1 to 1. A quadratic also has a domain all reals and a range of 0 to infinity. If we know that sine cannot live outside its range, then we can say the absolute value of x squared sine 1 over x cannot be greater than or equal to 1. So x squared sine 1 over x has to be less than or equal to 1. And do you remember when you talked about inequalities? It was less than, was and, great, or is or. So if you split an absolute value inequality that is a less than problem, that became x squared sine 1 over x is less than or equal to 1. And, because it's less than, x squared sine 1 over x had to be greater than or equal to negative 1. That's what the absolute value inequality told us. So if the function has to be less than or equal to 1 and greater than or equal to 1, it's fair to say that x squared sine 1 over x has to live between negative 1 and 1, which was the range of sine. But why do I care? Well, what we do then is look at x squared's limits. So because we've only talked really about sine, what's the limit as x approaches 0 of x squared? Not a trick question. It's 0. So if the limit as x approaches 0 of x squared is 0, and this function has to live within the range of sine, then it's fair to say that it has to also live within the limit bounds of x squared. So we're going to multiply by x squared on the outsides. So we have negative x squared and because we've applied our range, we've applied our things, the limit as x approaches 0 of negative x squared is 0. The limit as x approaches 0 of x squared is 0. Because it has to live between negative x squared and x squared, the limit as x approaches 0 of x squared sine 1 over x is also 0. So essentially what the squeeze theorem says is the range of the function that's undefined will determine the bounds. You use the limit of the function that is defined to find the value. And we're going to look at other examples of that to kind of help show it a little bit better. But we're going to look at those examples tomorrow, like we have an exploratory activity. Hey, where'd my homework go? Right, so you're using your textbooks once again. Yesterday we did 1 to 19. So for today, we're going to go back to the same page in the book. So we're going to go back to page 70 to 71. And we're going to look at .43. Let's do 43 to 49 odd.